So good morning, everyone. I'm going to give the talk on asymptotic density of graphs excluding a disconnected minor based on joint work with Rohan Kapadi and Sergey Narin. I gave a similar talk at Canada last month. Unfortunately, or fortunately, I finished it earlier than I should be. I tracked my heart rate during the talk, and I'm pretty sure at the peak is when I discovered that I finished my talk earlier, so hopefully this time I can do a better job at timing my talk. So a well-studied extremal problem in graph minor theory would be to find the extremal densities of graphs not containing h as a minor. So for a fixed graph h, let us define the extremal function of h to be the supremer over all ratios of h number to vertex number for all graph G not containing h as a minor. And we also define the asymptotic extremal function in a similar way, but for all graphs that the vertex number goes to infinity. And powerful extremal tools become available when considering large graphs in minor closed families, so, especially when we investigate C infinity of h rather than CH. Another remark would be that CH is always greater than or equal to C infinity of h, and if h is connected, then equality holds. Otherwise, it could be quite different. So I'll give you some easy examples so you have a bit better feeling of those definitions. So what is CK2? For all graphs not containing h as a minor, so they're ageless, so it's 0. And for all graphs not containing K3 as a minor are graphs without cycles, so it's fourists, so the value is 1. And in fact, we can obtain a lower band for clicks. It's because by this construction, it is a modified complete bipartite graph. One set has t minus 2 vertices, and the induced subgraph is a click, and all the vertices are in the other set. So when n goes to infinity, the density of this graph, the supremer, would be r minus 2, and it does not have kr as a minor because you will need at least r minus 2 vertices in the click. And in fact, Gabriel Dirac, Wolfgang Mader, Leif Jorgensen, Zixia Song, and Robin Thomas, they proved that the CK2 is exactly r minus 2 for r is smaller than or equal to 9. And Andrew Thomason proved that when r is large, it is quite different, and it is something with r square root of log r. So I'll use the same construction to show a natural lower band, but for a general h. So let tau h be the vertex cover number, and so it is the same construction, but s is smaller than tau h. And for this graph, h is not a minor of this graph. It's because the cover number, the vertex cover number of this graph would be s, and all minors of this graph would have smaller than or equal to s as vertex cover number. So h is not a minor of this graph, and thus you can have this lower band. So C infinity of h is always larger than or equal to, yeah.
What's the vertex cover number?
Vertex cover number? Yeah, so this is the largest set. It is the smallest set that the set that's G minus this one. There's like no edge. Yeah. So the natural lower band would be C infinity of h is always greater than or equal to tau h minus 1, and we call h is well behaved if equality holds. So let's go back to what we've done. So Kr is well behaved for r is smaller than or equal to 9, but it is far away from being well behaved for large r. But Andrew Thomason also considered skr, which is a union of s copies of kr, and it behaves similarly then with kr for fixed s. But when s is large, it is well behaved. So I'm going to show our results in the next slides, in the next few slides, and basically our results will imply that for many classes of disconnected minors, it is well behaved or close to being well behaved. So let H be the disjoint union of nanographs H1 and H2, and the first result would be a general upper band in terms of asymptotic extremal density function and also vertex cover number of its component. So in particularly, the second inequality would apply that if H1 and H2 are well behaved, then H is well behaved. So union of cliques of size no larger than 9 are well behaved. And another remark would be from the first inequality, we can obtain a strong form of Thomason's results for fixed S. So another thing would be if you replace C infinity by C for the first inequality, it is in general not true. But what about replace C infinity by C for the second inequality? So I asked this question before all those results when I was in undergrad, and I was pretty happy about it because it's not that every day you can ask Sergey a question that he's unable to solve in 10 seconds. And so Andrew Sokol, Aaron Lowe, Sergey Noren, Hehui Wen, Liana Yepriman proved a weaker form, a weaker result of this question. And I would also like to mention that Yan Wang and Hehui Wu proved the inequality is completely true. So from their theorem, they actually obtained the result for CH for disjoint union of cycles, which verified the conjecture of Bruce Reed and David Wood, Daniel Harvey and David Wood. And if you look at the right-hand side of this inequality, it is tau H minus 1 if H is a union of odd cycles. So a union of all cycles are well behaved. But in most other cases for union of cycles, the exact value of CH is undetermined. But our second result actually showed that, actually proved the exact value for C infinity of H for all unions of cycles. I don't have time to go into detail of this one because I want to come back to the union of large cliques. So as I've shown, Thomason's result, so it basically says that there is a turning point that when S is large, then there's turning points, then SKR is well behaved, but when S is smaller than this one, SKR is not well behaved, so we're interested in this turning point. And Thomason's result actually showed that the turning point would be smaller than or equal to R square root of log R. But on the other side, this result for KR, you will know that S0 is definitely larger than square root of log R, and Thomason mentioned in his paper that it is likely it is on the order of square root of log R. So we significantly improved it to be a polynomial in log R. And to prove this one, we actually used different techniques, including the probabilistic method and also the structure tool from Eppstein's, from one of the results of David Eppstein, which was also used to prove the other two theorems. So I'll probably just give a small idea of how we use Eppstein's lemma. So basically, it says that it is enough to consider fan graphs. And what is a fan graph? Fan graph is a GSK that when you have a G, you identify the vertex. It's like a proper subset of vertex S. And then S is a clique, and S, all the vertices of S is connected to some vertex in G minus S, and also G minus S is connected. And then you make copies of G minus S. So it will be a fan GS3, but you can obtain as many as you want, so it is enough to consider those graphs. One other example would be the extremal construction we gave would be the fan of when G is complete, is a clique on S plus 1. And thank you.